All right, welcome back to the Explainer. Today, we're taking complex syllabus jargon and turning it into a clear, structured game plan. We are diving deep into Cambridge AS and A-level mathematics. Specifically, we're cracking open the examiner's playbook for topic 3.5, which is integration by parts, for syllabus code 9709. If you're prepping for this exam, or honestly, even if you just want to see the exact mechanics of what top-tier math assessment looks like, you are exactly where you need to be. We're going to break down step by step exactly what the principal examiners are demanding from you. So let's jump right in.
Okay, 15. Why are we starting with the number 15? Well, because this single topic, integration by parts, makes up roughly 15% of your total marks for the Math 9709 exam. I mean, just let that sink in for a second. A massive chunk of your entire grade is literally riding on this one subtopic. So mastering this isn't just, a good idea. It is absolutely vital if you're aiming for the top of the curve. So here's our roadmap for today. We've got 4 main areas to hit. First up, core theoretical principles. Then, we'll look at the procedural framework. After that, critical analysis in practice. And finally, we'll go over some principal examiner warnings. Short, sweet, and to the point. Let's get to it. Section 1, Core Theoretical Principles, the foundation of top marks. You see, the theoretical architecture of integration by parts doesn't just exist in a vacuum. The assessment objectives are actually targeting very specific cognitive domains, your knowledge and understanding, your application, and your analysis. To really lock in those top marks, you've got to have precise definitions and a super deep understanding of the causal relationships within the math itself. Now, there is a massive difference between a standard candidate and a top-performing one. Standard candidates, they tend to have this very isolated understanding. They'll treat integration by parts as just some standalone trick, usually just blindly memorizing the formula. But the top performers, the ones really crushing it, they showcase cross-topic connections. The syllabus actually highlights this. Top students show a connected, conceptual understanding that they can successfully transfer to totally unfamiliar contexts and other syllabus areas. That right there is how you unlock the highest marks. All right, moving on to Section 2, the procedural framework. Step-by-step execution. When we move from theory into actual practice, tackling these exam questions demands a really systematic approach. The examiners are explicitly looking for strict conventions in how you present your work. We're talking proper headings, using the correct mathematical terminology, formatting things appropriately, and writing clear annotations. You literally cannot just throw a bunch of numbers onto a blank page and hope for the best. Your presentation is a massive part of the assessment. So, how do we systemize a complex problem when we're under pressure? You need a rigid sequence. Step 1, deconstruct the question, find the key elements and the relevant data. Step 2, pick your analytical framework and apply the right principles. Step 3, execute your analysis and do it with crystal clear working and notation. Step 4, verify your results, always verify. And step 5, present the final information in the appropriate format using the correct terminology. Having this exact sequence in your head is your absolute safety net when you're in that high-pressure exam room. But look, I get it. Remembering a rigid sequence while the exam clock is ticking and your heart's pounding, it's tough. It is so easy for your mind to just completely go blank. And that is where the visual story method comes in. This is an incredibly effective memory hack. You basically encode these complex integration concepts into a visual narrative. It's like turning abstract mathematical steps into a memorable, step-by-step story in your head. Do this, and you'll encode the process so deeply that you can retrieve it instantly, even when the exam stress is peaking. And really, this all boils down to the method mark strategy. Examiners actually award marks for seeing a verifiable analytical process and your clear working. They aren't just looking at the final number at the bottom of the page. You've really got to shift your mindset here. At this level, math is entirely about demonstrating how you think. If you clearly show your integration process, you're going to secure those vital method marks, even if some tiny arithmetic mistake messes up your final numerical result.
Okay, Section 3, Critical Analysis in Practice. This is about elevating your grade. This is exactly where you cross the line from average to exceptional. To do that, you have to push past just descriptive levels of math. The framework requires you to step up to analytical and evaluative levels. You need to be evaluating alternatives, comparing different mathematical approaches, and making really justified recommendations based entirely on the structure of your workings.
Whenever you're analyzing a tricky integration problem, try running through this mental checklist. First, identify any limitations in the data you're given. Second, note any assumptions that the problem scenario is making. Third, explore alternative interpretations. Fourth, evaluate the different integration approaches you could take. And finally, justify your conclusions. It's really all about showing the examiner that there is a deeply rigorous, professional mathematical mind at work on that paper. And that brings us to Section 4, Principal Examiner Warnings and the Pitfalls to Avoid. Honestly, this might be the most valuable part of our playbook today. Cambridge principal examiners look at thousands of papers, and they see the exact same patterns of failure year after year. We've pulled the absolute most critical pitfalls straight from their reports so you can make sure you don't fall into these common traps.
Here are the top 3 warnings. Number 1, confusing cause and effect. Do not mix up your variables and their relationships. A classic example in integration by parts is choosing the wrong functions for u and dv. If you don't use a strategic rule to pick what to differentiate and what to integrate, you're just making the problem infinitely harder for yourself. Number 2, forgetting to check format and presentation. Remember those strict conventions we talked about? Examiners literally deduct marks when your working is messy or poorly annotated. And number 3, providing generic answers without context.
I want you to listen to this definitive alert straight from a principal examiner. They said, the classic mistake is providing generic answers. Always link every point to the given scenario. Guys, this is huge. Even if your calculus mechanics are absolutely flawless, if you just write down a textbook definition or some generic math statement without actively applying it to the specific context of the question, you are going to lose out on those top-tier evaluation marks. Keep it linked, keep it specific.
So we've walked through the theoretical architecture, the step-by-step procedural framework, the higher-order analysis, and the traps examiners are literally begging you to avoid. So I'll leave you with this one question. Are you ready to connect your concepts, apply the method mark strategy, and actually claim your 15%? Go grab some past papers and put this playbook to the ultimate test right now. Thanks so much for joining me on The Explainer today. Keep learning, stay focused, and keep it structured.